So we know it's a cylindrical can, so I start by making a picture. I know the volume is going to be 1,000 cubic centimeters. I need to figure out an equation then for that volume, where I'm going to do 1,000 equals that. In order to do that, I need to write an equation for it, so I need to actually have my dimensions labeled. When it comes to volume of a cylinder, we need to know what the radius is, and we need to know what the height is. Now, a cylinder, you could also describe it as a circular prism. That is, where we take whatever the shape is that's on the bottom, in this case a circle, and we extend it straight up. All of those prisms have the same equation for its volume. It's the area of the base times the height. That gives you a way to help remember this, because the area of a circle then is pi r squared. And so I would multiply that then by the height. And there's my equation for my volume. That's the one using the number that's involved. That's always the first equation we write. The second equation we write, because yes, we are going to need a second one, is going to have to be for whatever we're trying to maximize or minimize. In this case, we are trying to minimize the cost of the metal to manufacture the can. So if I want to minimize the cost, that means I need to minimize the amount of metal. Well, the metal then would be the surface area. So we're going to be trying to minimize the cost of the metal. I'm going to call it M for metal.
Oh.
You certainly could have called it S or A or something like that as well for surface or area, whatever. It's not particular what you call it. It's just a matter of calling it something that means something relevant. Now, how do we find this surface area then? Well, two of them are pretty easy to find because it's the area of the bottom and the area of the top added up together. The area of the bottom and the top are both pi r squared, and if I have two of them, it's going to be 2 pi r squared. Plus, now I need the area that's going around. So this part here. So a way to think about this. Now, there is a formula that you can memorize, but let's say that you forgot the formula and you have to actually figure out what this is. Let's say we take this part that's wrapping around the outside, we cut it and lay it out flat. Yes, that's a rectangle then. And so that whole thing ends up being a rectangle with a height of h. But what would this length be? Yep, that's the circumference. Because it has to wrap around the outside of the circle, which is 2 pi r. And so it's plus 2 pi r h. Now, you're saying, well, I could also write it as pi dh using diameter. Yes, but then I'd have an extra variable in there, and I don't want to deal with extra variables. I want to minimize the number of variables. In fact, remember, that's why we write our two equations. Because I write two equations because I'm going to want to take this first equation and solve it for one of the variables. Hint, h is going to be easier. Yeah. And then plug that into the other equation, so then we have just one equation where m equals something in terms of just one variable. That way we can find the derivative and have it be useful. So now once we found out what h is, I plug in what h equals into my equation, and then I want to simplify that. Now notice when simplifying, I'm going to be multiplying this pi, and I'm dividing by that pi. So they're going to cancel each other out. This r would end up on the top. I got an r squared on the bottom. So I'm going to be able to cancel out r from the top and the bottom. Although notice that will leave an r in the bottom still because it starts out as r squared. And so I do the 2 times 1,000, which is 2,000. The pi's cancel, remember, and so all that's left on the bottom is just r. And now that we have that, this is the equation that we're going to find the derivative of, and then we'll set it equal to 0. So, find the derivative of this equation now, set it equal to 0 and solve. So when we solve that through, we get down to r cubed equals 500 over pi. Of course, then to get what r equals, we're just going to take the cube root of that. Remember, when doing cube root, you don't have to worry about plus or minus, so that's not an issue here anyway, even if it would come up in the context of the problem. And so we have the cube root of 500 over pi. Now that is something that we can go ahead and calculate, right? And so, in this case, that's kind of ugly, right? 500 over pi and then taking the cube root of it. Because it is that way, I'm going to go ahead and actually calculate this out as a decimal. When we do that, we get about 5.42. So that's the approximate radius. Of course, we do know the exact radius here, but we can go ahead and use this for our approximate value. Now, let's go back. Remember what this question was asking for. We want to find the dimensions. Notice. So if I'm looking for the dimensions, well, I got the radius, but I still have to find the height. So to find my height now, remember I have an equation that just tells me what height equals. So I'm going to plug into that. We're now skipping out of optimization problems, and we are now heading into a little bit more work with limits, finding some values that we otherwise might not have been able to find. And we're going to start by practicing with what we already know about limits. So please take a moment, find each of these two limits. Yes, these are both doable based on work we did previously. All right, so taking a look at each of these, when we did limits before, remember, the very first thing we would always try is just direct substitution. So I'd try plugging whatever x is approaching in for x. But of course, in this case, notice that if I do that, that would just give me 0 over 0. And we don't know what 0 over 0 equals, right? Because we can say 0 divided by anything is 0, but anything divided by 0 is undefined. And so it creates a indeterminate form, to use a fancy word there. But in this case, we can do it because we can simplify the fraction first. Yeah. So if I simplify the fraction by canceling out the x's, I actually end up dealing with the limit as x approaches 0 of just 8 over 1, or just 8. Yeah. Well, there, if you substitute 0 in for x, there is no x, so obviously that's just going to equal 8. Yeah. And that's our final answer. That's what we're looking for. Now, the second one over here, as I take a look at that one, again, I start by trying direct substitution. And you notice I'm bringing it back to that. We always still have to start by trying direct substitution and checking it. If I plug the 5 in for x in both of these, 5 squared is 25, 25 minus 25 is 0. On the bottom, 5 minus 5 is 0. It ends up with another one of those 0 over 0 situations, which is why we then have to try simplifying. Now, of course, we can simplify it here because this factors. That becomes x minus 5 times x plus 5, meaning that then the x minus 5s cancel each other out. And so the whole thing is actually the limit as x approaches 5 of just x plus 5. Then I can do direct substitution. 5 plus 5 is 10. And there's our answer. Now, notice with these that when I ended up doing these, basically what I just proved is that 0 over 0 can equal 8. And that 0 over 0 can equal 10. Oh. It can be some weird stuff going on here. And it's this weird stuff that we're looking to deal with today. Because 0 over 0 is what's called an indeterminate form, particularly of the type 0 divided by 0. The value of 0 divided by 0 will change when we're finding limits based on the original equation that was involved. And so what we're going to be looking at today is some ways to do this type of problem where we can't use some of the methods we looked at earlier. Because, of course, we've used the methods already that we have learned earlier. Factoring, canceling, things like that. Well, today we're going to learn a new rule for that. Now, the rule that we actually have for this, it was invented by a French guy. And like so much math, if you actually come up with a rule, you can name it after yourself if you want. And so the guy's name was L'Hôpital, or at least I think that's how you pronounce it. I don't know French, but I've tried trying to figure out how to pronounce it correctly.
El Hospital. What are you guys talking about?
This, we'd say it is L'Hôpital's rule.
No, that's El Hospital.
Okay, please write this down into your notes now.
All of it?
Yep, all of this. Except, of course, leave a little blank space where I got the gray box here, because I'm going to be adding something to your notes later for that part. Now Now, one little note though, you notice this rule has some fine print. We could spend lots of time just looking at the fine print and trying to explain it, but I just wanted to tell you about it and make sure that you know there is some other details that are involved with this. But for the time being, really you just need to know this stuff up here. The stuff in red, that's just extra information you can have. I wrote this here just to help you see. I'm not taking the derivative of f over g. I'm taking the derivative of f and then the derivative of g separately. So it is not a quotient rule problem for that reason. And so what this is telling us then is that if the limit as x approaches a of f of x is 0 and the limit as x approaches a of g of x equals 0. In other words, if when I use direct substitution here, it would have given me 0 over 0. Familiar situation, right? That's where we started this part. If it gives us the 0 over 0, then I can use this rule by finding the derivative. But this is not like a catch-all. This doesn't work if it doesn't start that way. If it is not an indeterminate form. If we can find it using one of our other methods, this rule might actually give us the wrong answer. So it is very specific to you have to check and see if you can use the other methods first. Now these are some examples of some types of problems that we're going to be doing here soon. Each of these can be done with L'Hopital's rule. The thing that I want you to notice about them is that all of them can equal different things. And they all come from limits. They can be approaching different numbers along the way as well. But every single one of these, when we start off, if I just plugged in those numbers, it'd give me 0 over 0. Which is why all of these are examples that will use L'Hopital's rule. We're now going to go ahead and start this process off with this one, because we've got to practice this rule a few times. So, when approaching a problem like this, the first thing we need to do is try to find the limit without using L'Hopital's rule. We're still doing it the same way that we've done it in the past. So, we would try with direct substitution. If I use direct substitution here, if I plug in 1 for x, what do I get on the top? 0. If I take the 1 and plug it in on the bottom, what's that give me on the bottom? 0. So already that rules out direct substitution. I can't use direct substitution on this. Can I factor and reduce? Well, can I factor that?
Yes.
Yes, actually. That's a difference of cubes problem. So, can I factor this? Not so much. So, I'm not going to be using the factor and reduce method because I can't factor both of them. And so no reducing will happen. Multiply by conjugate. Remember, that's what would happen when we had like the 1 minus the square root on the bottom. Remember those types of problems? We'd multiply by the conjugate there. Obviously, this is not set up for that kind of thing.
Oh, no.
And then combining fractions, that's where we'd have the fractions within the fractions. And this one's not set up for that either. So, that tells us that then, yes, we will go ahead and use L'Hopital's rule. Step 1 for finding L'Hopital's rule is to find the derivative of the numerator and the denominator individually. So, please, go ahead and find both of those derivatives real quick. And yes, they are quick because they're both polynomials. Now, when you do that, it's then the limit as x approaches 1 of those two derivatives. And so this is now what you would write for your first step of actual work on this. Is you would write that we now have the limit as x approaches 1 of this equation. And again, I got that equation by taking the derivative of the top and making that my new top. Then the derivative of the bottom, make that the new bottom of the fraction, the new denominator. All right. We now, in its own way, we are now restarting the problem. So I now look to see, can I just use direct substitution?
Yeah.
If I plug in 1, what's that give me on the top? Negative 1. Okay, so it's not a 0, so I'm heading in the right direction. So it's going to be negative 1 over. What do I get on the bottom?
3.
3. Okay. Then, the answer then is negative 1/3. We figured out the limit using L'Hopital's rule that we could not have figured out otherwise. Now to picture what's going on here, if I made the graph of our original equation where we found the limit, you'll notice at 1, this is the point. We actually have a hole at that point, and it's down here at negative 1/3. And so that's what that was telling us, is where the graph was approaching from those sides. All right, let's repeat the process now that we got the idea. Please go ahead and write down this problem and find the limit. All right, so again, we jump into the process of finding the limit. And again, remember that the first step in finding our limit is try to find it without L'Hopital's rule. So direct substitution, if I plug in 2, I get 0 over 0. Okay, so I can't just use direct substitution. Can I factor it?
No.
Yes. You'll notice that I can factor the top and bottom here, and this would actually become, the limit as x approaches 2 of 1 over x plus 2.
I'm going to, yeah. 1/4.
And then I can use direct substitution and get 1/4. You didn't even have to use L'Hopital's rule here.
You got it.
All right, so first thing we do is we try to find the limit without using L'Hopital's rule. Direct substitution. So let's try direct substitution. If I just plug the 1 in on the top, 1 squared plus 1 is 2. The natural log of 1 on the bottom is 0. It's 2 over 0. Remember, L'Hopital's rule only works when it's 0 over 0. L'Hopital's rule does not apply here. So what is happening with this limit? Well, take a look at the graph here. You'll notice that as we're approaching 1, we're approaching an asymptote.
It's asymptotical.
And so in this particular case, the limit does not exist because it's different from the left and from the right. So first thing I want to do is I want to try finding the limit without L'Hopital's rule. So that starts with direct substitution. If I plug in the 0 for x, well, e to the 0, remember, is 1. Minus 0 minus 1 would equal 0. So this would give me 0 over, and then cosine of 0. Yes, you should know your unit circle for at least something like that, right? Cosine of 0 is 1. 1 minus 1 is 0. So this does look like it might be a candidate for L'Hopital's rule, but of course that was just by trying direct substitution and saying that that one didn't work. Is it factorable? No. Can we multiply by a conjugate? No. Can we combine fractions? No. So yes, we must use L'Hopital's rule for that reason. And so we find the derivative of the top and the bottom. Now, as we do so here, it stays the limit as x approaches 0. On the top, I'm going to do the derivative of whatever is on the top. The derivative of e to the x, of course, is e to the x. Minus the derivative of x is 1. Minus the derivative of 1 is 0, so that just goes away. On the bottom, derivative of cosine is negative sine. And again, the derivative of 1 is 0, so that just goes away. Okay, now that we've done that, it's like we start the process all over again. I now try direct substitution. If I do direct substitution at this point, e to the 0 is 1, minus 1 is 0. Okay, on the bottom, what is sine of 0? Sine of 0 is 0.
So we got to do it again.
So that's negative 0. Okay, so
Wait a minute.
it is
Hold on,
like
Turbo.
it is like we then are starting the problem all over again. So if I just ask you to find that limit, well, we just found out that it's 0 over 0. We check our normal things. No, it doesn't factor or anything like that. So I use L'Hopital's rule again. And so then I'm going to have the limit as x approaches 0. Find the derivative of top and bottom again. All right, so when we find the derivative of top and bottom from that one then, okay, now things are looking simpler. Let's try direct substitution again. We're plugging 0 in for x. E to the 0 is 1. Okay, so we already know that we're going to end here. We know we're not going to have to find the derivatives again. And on the bottom, the derivative of not derivative of cosine. Cosine of 0 is 1. And we make it negative, so that's a negative 1. So 1 over negative 1 is negative 1. And so that's what we're approaching there, is negative 1. And just because it is fun to see what some of these crazy graphs look like, this is what we just did, is we just found that value.
Oh, wow.